All right, so before we dive into the new lecture about sorting, we'll do all sorting today. Maybe a little bit singly linked list, a little bit introduction at the end. We'll see. Before that, so quick reminder, your assignment number 1, solution has been released. And if you've got any trouble following through the solution, let me know. But I will really highly recommend you try to re-download the starter code again and redo it. That'll be the one way to practice, just more problem solving. And split array harder, I just want to delay a little bit longer for the solution release, and I really want you guys to try, even if that's imperfect, right? Just reach out to me if you want to discuss the idea. And one thing here that's kind of, for those of you who are interested, I'll just show you once. I don't need to trouble you for later. So under the lecture site, so now for lecture from today and onwards, you will see 2 links to the notes, right? Usually this one here will be the annotated version, which I will post after class, obviously. The other one, for you guys, it will be section X right here, right? So if you click on the other one there, so that'll be the clean version of the notes. So if you want to download it to your iPad, tablet, or if you want to print it out to take notes, be my guest. So I will try to make this available at least 1 hour. So you guys have some advantage since I made this available to the morning section. So guarantee before the evening class, it will be there. But take advantage of that if that can help, right? So I may not bother you with any more announcement about it being ready. So I would say at least 1 hour ahead of the class. For you guys, maybe a few hours before. It's there, right? Just use it, make use of it whenever you need to. All right, so let's now go back to some recap. Before that, guys, any question about the course? All right, good. And again, for assignment number 1, I'm going to rely on you to really catch up any gap with the learning and let me know if you got any trouble. Okay, let's now talk about some recap very quickly, and then we'll continue. All right, so last time we basically tried to apply the big old knowledge about asymptotic upper bounds into Java code. And we'll do something very similar today. But today we're going to do something even more valuable, which I'll get to. So this is one is easy, just constant. And this one here, just linear. The more interesting one is about when you got nested loop, in which case the essence of the solution is to really observe the patterns of the loop counter, enumerate them, and add up together, right? So that will be the way to go. And we're going to see more examples like this today, okay, for the Java code. And you can follow the detail from the lecture recording from Tuesday. And this one is to say, you got to really watch out for the bounds of the loop counter. When you got double nested loop, it doesn't necessarily mean you're going to get n squared. Not really. You might end up getting linear. You might also end up getting constant. Really depends on how the bounds are set up. All right, and then, yeah, we talk about some other discussion here. You can also refer to it. And this one here, just to say, if you are given a piece of code, one way to really guess it very quickly is to identify the parts that is going to be dominates over other parts. So that's really about to find which part is going to be the most expensive one, which will take the most time to execute. In this case, it will be n squared. So overall, it's going to be n squared. And there's a last example here, which will get some nice triangular shape over here. And we're going to see that for one of the sorting algorithm for today. We'll see. Okay. So there's a very useful pattern here. And also the general approach we're adopting is to observe exactly how the loop counter I and j are going to change accordingly, and then add up things together. And we're going to see the so-called arithmetic sequence very often. So we also spoke about it last time. And for another sequence called geometrical sequence, we're going to talk about it when we talk about trees after the reading week. But for now, this is what you should know about a summation. Okay, we'll apply that maybe for more examples for today. And that's the last example we talk about. So for array, you just got to remember indexing is very efficient. And also, if you want to do some assignments into the array, it's also very efficient. What's going to be expensive is really about insertion and removal from the array. So the example we did is about insertion. So here is why it is inefficient. Let's say this. We got this input array. And let's say we want to somehow insert a new element into index 0. What does that mean? That new element should go to the new array at index 0. But what about other stuff? Conceptually, we are shifting everything here, for example, 0 to index 1, 1 to index 2, 2 to index 3. So we're shifting the whole block to the right by 1 position. To do this correctly, you have to do it systematically using a for loop, which is going to take linear time. So that's why it's expensive. So this is something this is actually why I want to talk about this example here. For one of the algorithms that we're going to talk about today, for sorting, this is a critical step, which is going to cause the running time to somehow be not as efficient as others. All right, so that's something you can also keep in mind. So from this example here, you want to know several things. Number one, just given this piece of code without understanding the logic, can you derive the asymptotic upper bound and justify, like how we did it, right? I just did it individually by writing out the logic, right? Number one. Number two, are you able to trace it, right? I might also ask you maybe during the test, for example, what this assignment here, what exactly that means, right? What you will do exactly. So that tracing part is also very important. I'll also give you guys some a little bit more challenging exercises to try it out, also with the solution. You can also take a look. And that's it. Any question from Tuesday? All right, if no, let's now do sorting. So today, we're definitely going to do 2 sorting algorithms. That's really the plan. And the sorting problem here, and just going to conform to the computational problem format. We got input and we got output. So here we say input is going to be an array of n numbers. And we want to return the output, basically the same array, but it has been sorted according to the so-called non-descending order. All right, you may have seen this term before, but now, even before we talk about sorting algorithm specifically, I want to clarify this term very quickly and do some exercise together with you. Sorting problem may require different sorting order. All right, so you got to watch out. So there are at least these 4 possibilities. Non-descending, which is what we're having. Ascending or increasing. Also non-ascending, and also descending or decreasing. Right? So these are the 4 possibilities you might see for your sorting algorithm. Of course, given a particular one, you have to adapt your algorithm accordingly. Usually, it will not be very difficult to go from one order to another, but you got to know exactly what it means mathematically. That's something I want to do first, and then do some exercise with you. All right, let's now take a look at these 4 orders, right? They are very straightforward, but you just got to know the definition very thoroughly. All right, so I got these 4 possible sorting order. I got decreasing, descending. I got increasing, ascending. Let's talk about these 2. These 2 are very straightforward. Decreasing, descending simply means the values of the array should have this downward trend. All right? Let me write it down here. That means it should be this downward trend, always downward, strictly decreasing. And if you say this is element at index I, its immediate to the element to its immediate right. Let's say a I plus 1. So in this case, we should have the larger than relationship, right? AI should be exactly strictly larger than I plus 1. One example. 5, 4, 3, 2, 1. And if you look at, for example, 4 and 3 over here, you can see that's exactly the larger than. Easy. Symmetrically, when we talk about increasing, ascending, it will be just the other way. It's going to be the upward trend rather than downward trend. So that one there, let me also write it. Okay, upward trend. So this will be, for example, AI to its immediate right, AI plus 1. Right? Obviously, that's going to be smaller than. Notice that there's no equal sign. Right? One example will be 1, 2, 3, 4, 5. And you can see that, for example, 2 and 3 over here is exactly that smaller than. The smaller than relation should really hold for every consecutive elements. The tricky ones will be these 2. The way to think about it is being a little bit more logical to derive what's really happening here, just in case you forget. Let me just use the non-descending as the example over here. Okay, so this one here, non-descending. Okay, the way I see it is like this. When I say non-descending, the non here really corresponds to the logical operator for negation. not the case, descending. All right? So the way to work out the logic is, okay, by definition, it will be not the case, descending. And we just learned that for descending, which will be this case, it should be AI strictly larger than AI plus 1, right? Let's apply that. Equivalent to, not the case, AI larger than AI plus 1. Now we can distribute the negation over larger than. I'm pretty sure you know. That should be less than or equal to. Equivalent to AI less than or equal to AI plus 1. So this is the formal definition for non-descending. And you can work out the logic for non-ascending in a similar fashion. I'll leave that to you. Very straightforward to derive that. Based on this, let's now visualize it quickly. Okay? So now we got non-descending over here. How do we visualize it? This is to say it just cannot go descending. As long as you're not really trending downwards, you'll be okay. What does it really mean not to trend downwards? You can either trend upwards or no trend, flat. These are the two possibilities. All right? So I'm going to write it down here. So it could be, for example, trending upwards, or it can be flat, or it can be trending upwards again, right? Like that. So if you think about maybe this is A at index I, this is A at index I plus 1, and this may be A at index I plus 2. Right? You can see this one here is less than, and this one here is equal to, right? Exactly corresponding to less than equal to over here. All right? One example. 1, 2, 2, 3, 4. 1, 2, 2, 3, 4. Right? Obviously, you can see the 2, 2 over here is the equal, the flat. And also maybe the 3, 4 over here is the example where we're trending upwards, less than. All right? The last one will be just symmetric. Okay, let me just write it down for completeness. That one there is simply just going to be larger than or equal to. All right? So as long as we are now trending upwards, we'll be okay. So we can either be trending downwards, stay flat, or trending downwards again. Okay? So now if you try, let's say A at index I, so this will be A at index I plus 1, and also here A at index I plus 2. Let's see. So this one here is less than. This one here is just equal to. Okay. Oh, sorry. I really meant to put this guy here to exactly here. Okay. Sorry, it's a bit mess. AI plus 1, less than. AI plus 1, AI plus 2, equal. All right. Hey, let's see one example quickly. And the one will be 4, 3, 2, 2, 1. 4, 3, 2, 2, 1. So you can see again, this will be the equal here. And this will be the trending downwards. Like that. All right, any question about the definition? Yeah?
So what if you wanted to sort in a decreasing or increasing way list or an array that has duplicates? Would you get rid
That's a good question. That's a very good question. So now there's some very important insight which I'm about to say. Apparently, you can see for decreasing or increasing case, the array should not contain any duplicates, in which case it got flat. It should not be allowed. So that would be so-called a precondition for the input. If the input itself already contains duplicate, it should not be valid even. You don't really want to remove the duplicate for the input. Yeah. Oh, we'll talk more about it later. Just bear with me one moment. So here, so the for decreasing and also for increasing, so these two, there'll be no duplicate allowed. On the other hand, for the non-descending and also non-ascending, these two, duplicates will be allowed. Duplicates allowed. Specifically, duplicates for consecutive elements, because you stay flat, right? Question somewhere. Yes?
first time, would you do it in a decreasing or increasing?
You know, I would say for sorting, you know, it really depends on what you need. You know, let's say for student record, right? Sometimes you may want to see from the maybe highest performance to the lowest performance. Sometimes you may want to see the other way. It really depends on application. Nothing wrong with either one of them.
So learning it for the first time, would you want to do ascending or descending? Would it not matter?
Doesn't really matter. But you know, just say for the selection sort, insertion sort we're going to talk about today, we're going to do non-descending. Yeah, non-descending. Yeah, just get used to the term. That's my point, right? Yeah, guys. So in the test or exam, either of these four is possible, right? You got to be very clear about which one is which, right? That's why I really want to spend time making sure you're fine with this. All right. Any question about the basic definition? Question for you. There we go. Oh, again, you know, this is really unfair to you guys. I forgot to include that again from my notes. Okay, that's really unacceptable from my side. Okay, just give me one moment. So there is really a problem which I want to solve together with you. Just give me one moment. I'm going to get it in within 10 seconds. Okay, this is one here. Somehow it's lost. Okay, bear with me. So let me just retrieve here. There we go. There we go. I'll make sure I double check the notes before I present for a second section. It should not happen. Yeah, I'm just copying that. Bear with me. Basically, the exercise I want you guys to try is to think about two sets of array, and then to decide how can we formulate a relation between the two, right? As soon as the copy is done, and then I'm going to show it to you. Sorry, take some time. Okay. Almost there. Okay. All right. Good. There we go. And then I'm just going to just clear that. And then this will be completely clean. Okay, again, my apology. There we go, exercise. All right, so here we got two sets over here. And set number one, S1. That one contains all the possible arrays sorted in the non-descending order. Set number two, all the possible arrays sorted in ascending order. All right, try to recall the definition, right? Exactly, right? So now we got set one and set two. Conceptually, they're infinite because there are infinite number of arrays that may be sorted in a particular fashion, right? Now we want to formulate the relation between these two sets. What would be the symbol to use? Or if you simply think there's no relation between them, maybe the intersection is simply empty. That's another way to say it. This is a very nice one to test your understanding about the definition. Of course, if you're still getting used to it, that's fine, but I just want to see if anybody would like to suggest anything. Okay, I'll pick one here. Go ahead.
Would S2 be a subset of S1?
Are you suggesting something like S2, subset?
Sorry, would it be proper subset?
You tell me.
Yeah, it'd be proper subset because not all non-descending.
Okay, not bad, not bad. Maybe that's what you're thinking as well? Okay, good. So guys, pretty good. Your fellow student was right, but let me elaborate on why this should be the answer, right? It's okay if you're still getting used to it, but think about different combination, right? I might ask you different combination, right? So this one here is actually correct, but we're going to see exactly how this is the case. Whenever you want to show proper subset, okay, this is what you got to show. So let me just make a little bit color here. So let's say S2 is over here. And also S1 is over here. All right. So let's say S2 is a strictly smaller set, and S1 is a strictly bigger set over here, right here. Okay. And then we're saying that S2 are all the arrays sorted in the ascending order. So this will be about ascending. Versus S1 over here would be in the non-ascending order. S1 in the non-ascending order. If we claim that the relationship should be proper subset. Hmm? Non-descending, yes. Oh, I said non-ascending, right? Thank you so much. I definitely didn't mean that. Thank you. Thank you so much. Yeah, for sure. Right, so now if we say that it should be a proper subset, what does that mean? That means there should be at least one member over here we can show that belongs to S1 but does not belong to S2. All right? So that's the member we ought to show. There is an array in that's actually in S1, but it is not in S2. All right? Give me one example. What would be such array like? All ones? Okay, I like that. Basically, it's not really, it's not just strictly increasing, basically. For example, 1, 1, 1, and 1. Thinking this way, when we talk about ascending, right, it should be the less than relation. When we talk about non-descending, it's really the less than or equal to relation. So what really stands out in S1 is about the equal sign here. So if you got any consecutive element that actually shows you the flat curve, that would not belong to ascending. All right? Question about this? Okay, I hope that's straightforward. That's important, right? So just get ready for different combination of the orders, right? You really want to see what's the relationship between different orders. Which one, for example, this one should be more specific and this one is more general, right? About non-descending. And we're going to do non-descending sorting today. All right, good. All right, if no further questions, let's now move on to the slides. So what we'll do is we're gonna consider two possible sorting algorithms, namely selection sort and insertion sort. We're gonna talk about one by one, and then we're gonna compare, of course, their time complexity. Okay. The way I'm gonna do it is I'm not gonna show you Java code just yet. The way I'm gonna show you how they work is by visualizing their steps, and this is a very valuable lesson for us. In order for you to design your algorithm, you just don't need to write any code. All you got to do is to be very clear about how the flow of the algorithm is going to go and be clear about the running time for the critical steps. That will be enough for you to derive something that's reasonably accurate about the asymptotic upper bound. So I'll do that first for insertion sort, selection sort, show you how they work visually, generalize it visually, and then derive the bounds right from there. And then we'll see some Java code at the end. Okay. To some extent, Java code is not too much of the focus right here, right? That's important to see. All right, so let's talk about selection sort. And so these two bullet points actually summarize about the essence for selection sort, but we'll go over that together. Selection sort basically, well, from its name, selection. So keep selecting stuff, and then do it iteratively. All right, that's something we're gonna see. And let's now go with selection sort. Okay, let's now do some example here. So let me just talk about the critical step that we're going to keep doing. We're going to keep selecting minimum value from the unsorted portion and also appending it to the end of the sorted portion. So you can see we've got the notion about unsorted portion and sorted portion. The notion is easy to see. The input itself, presumably unsorted. every element there belongs to the unsorted portion. That's why I highlight all of them to be red. What we want to get to is eventually after the sorting algorithm is done, everything here should be appear in green. Right? So that's what we're going to see. Okay? And then let's now just learn the steps just by example. Now we just got 4 elements in the array. And initially you can see there's no green. So that means the sorted portion is simply just empty. We don't see that. Okay? After the first step, we're going to grow the sorted portion by 1 element and shrinks the unsorted portion by 1 element at the same time. Okay? So let's now talk about the first step. We're going to select something. Okay? So the idea will be, so from the entire unsorted portion, we're going to select the minimum. Obviously, should be this one here. Pretty much like a find max, but now we say find minimum, right? So this will be the minimum. So here I would say select the minimum from the range of the array from 0 to 3. From A0 to A3. Okay, that's what we're going to do. And once you select the minimum, what you're going to do is you're going to append it to the end of the sorted portion. Okay, so now imagine this. Basically, think about what we're having is the sorted portion is not there just yet. But to really put it there, you can do some simple swap. Okay, and swapping is simply just about variable assignments. If you do swapping, it's going to be a very cheap operation to do. So selection is more expensive than swapping. That's something you can keep in mind. So we don't need to worry about the implementation detail about how exactly a swap is going to be done. But let's now do that. So what's going to happen is I'm going to just draw another array here, and then to show you the outcome for the first step. All right, so that will be the resulting array. So we somehow is going to move move 1 here into the leftmost over here. That's going to be a sorted portion. And then 3 here is going to be swap over here. All right. So we're going to do some swap. Think about, we'll do some swap over here. So 1, 3, and 4 and 2 remain the same. So what we got is we got 1 here. And we got 3, 4, 2 over here. That's the first step. You select the minimum from the red area and then append it to the end of the green area. Okay. Let's do one more. And then if I want to do the next, just before I show this one here, okay, just before that. The next step will be we want to select the minimum from this area here. You can see the area getting smaller and smaller, basically, right? Let me do this, and then we can make some mini observation. So this one here, we're going to select the minimum from A1 to A3. Notice that you can see the starting point is getting more and more to the right. So that's why the search area is actually getting smaller and smaller. And the minimum is 2 over here, right? So now how do we actually somehow conceptually move this 2 here to just the last element to the sorted area? How do we do that? You can do a swap. You can, for example, swap these 2 elements. That's going to do it. All right? So I'm going to do some swap over here. Okay? And then the resulting array is going to look like this. So what I will get is I'm going to get 1 and 2. So that will be considered as sorted. Versus, so think about the 2 will be here and 3 will be here, right? After swap. So that maybe we got 4 and 3. 4 and 3 here. All right, any questions so far about selection? Right? As you can see, each time after every step, we are trying to grow the sorted area by 1 and shrink the unsorted area by 1 at the same time. Okay? Let's do the next step. Okay? And that will also make some observation. The next step, we're going to again select the minimum from, Now this time will be starting from A2 and all the way to A3, right? That's the unsorted area. A2 to A3. And that's the starting point here. And if you do that, basically over here, so the minimum would be 3 right here. And we want to append this 3 to the end of the sorted area. To do that, we can simply swap these two elements, right? So we're going to get 3 here and 4 here. 1, 2, 3, and 4. And 1, 2, 3 will be the sorted area, and then the 4 is the unsorted area, right here. You can see now the array is sorted, I agree, but just for our convenience of analysis, let's do one more step, which will be constant somehow, right? Anyway. And that will draw some conclusion before we generalize it. So the last step will be, we want to select the minimum from A3 to A3, basically, just one element. You can think about the portion has only one element there. From A3 to A3, okay? There we go. Okay, and then what we get is 1, 2, 3, 4. So everything will be green. So 1, 2, 3, 4. That's selection sort. Any question about individual step, right? You can see I've done that a few times, right? A number of times. Select and then append, basically. Let's make some observation, okay? Number 1, how many steps do we have to do in total? Let me delete this. I also delete this. You got a question? Okay, go ahead.
Is the last step really necessary?
The last step, if you want, if you go to the implementation, it may be omitted for efficiency reason, but it's only one iteration, right? Yeah. But here, just for convenience for us to count conceptually, it's okay to include it. Okay. Yeah, good. Okay, so number 1, we want to know how many steps are there in total. So this is one step, this is one step, this is one step, this is one step. In here, we got 4 steps. But what about in general? Number of steps. That's the first question. The way to see that is, every time you perform one step, you're going to grow the size of the sorted area by 1. Given that the sorted area is starting from empty, you want to grow it all the way to the entire array. So that should correspond to the steps, the number of elements in the array, right, conceptually. It could be n minus 1, but let's say n for now. It's easier for us to do analysis. So it will be the size of the ultimate sorted portion, which will be n. Right? So this is something very important to work out first of all. Right? It's going to help us count later. All right, another observation. Are all the selections over here equally expensive or equally cheap? If no, then what's the trend over here? Which selection is kind of the most expensive and which one is kind of the cheapest, right? The first one is the most expensive or the cheapest? Most expensive. Yeah, good. Selection. The first one, you got to select from the entire array for the minimum. That's going to be linear for sure. The second one here, you got one element less. It's like n minus 1. Still kind of linear, but you got to decrease all the way to, in the very last step, when you want to select the minimum from here, just 1. All right? So we got decreasing cost. Of select. Okay, I'll just decreasing for now. You know what decreasing means, right? So this, I'll say decreasing for now, but when I generalize it, we'll make it even more precise and count. All right, so these two are the very important observation. And before we start deriving the asymptotic upper bound, let's now generalize it once more. Okay, we can make it even more precise for you. Here we're only talking about this like an input array of size 4. Let's talk about in general. So for selection sort, insertion sort, once you have gone through one example, you got to generalize it to count, to approximate. So I'm going to show you two possible ways to approximate it. You can choose whichever way you like. One way is more visual, which I'll do in selection sort. I can start with an input array of size n in general. I'll put n here just to say its size. In the beginning, every element there is unsorted, so I'll use red, like a pink here. When I do the very first step, right? The very first step, I know that if for me to select the minimum, it's going to take n, because I got n element to search for the minimum. On the other hand, when I want to append to the end of the sorted portion, it's always about swapping the elements. Exactly how you swap, you can look at the Java code, which will be part of the exercise I will assign to you, right? Append to the end will just take 1, just about swapping, okay? And after this one here, after the first step, I'll just do maybe one more step before I say ... After this one here, the sorted portion is going to be of size 1, right? So I'm going to say 1 here. Okay, so over here it's going to be 1, and over here is going to be, this one here is going to be n minus 1. So n minus 1 here, and also 1 here. Right, next step, just one more step. If I go for one more step over here, if I want to select the minimum, what will be the cost? N minus 1, right? That's the shrunk version of the sorted, unsorted area. N minus 1. And also append. Okay, 1 here. And then what I will get is something like this. It will be just array size remain the same. It's just the portions are dynamically changing. Okay, so over here I got 2. Okay, think about 2 here. So I got 2 here, and then I got n minus 2 over here. And then I can say now, ... All right, so let's now see what would be the last step. Let's now visualize that. The last step is going to be something like this. Okay, for convenience, let's say the last step is going to be when the unsorted portion got exactly 1 element left. Okay. So over here we got, just here. So we got exactly 1 element left. And then we got n minus 1. Right? So here we got n minus 1 over here, and we got 1. Unsorted. And in order to really do that last step, let me draw a little bit better over here. That one is supposed to be just ... Okay, so now to complete the very last step, we're basically just going to do some selection, but that one here is going to be the cheapest because the unsorted portion is almost done, almost gone. So to select the minimum is going to be just 1. And the append, always 1, just about swap. After that, we get exactly just n element here being sorted. There we go. All right, that's a generalized view. All right. And then, how many steps in total? So here, the number of steps, right? Step number 1, step number 2, all the way to, right? What will be this step? Because you can see that we got n here, n minus 1 here, all the way to 1. Right? If you count that, it's going to be n steps in total, corresponding to the size of the array, right? You can see the pattern here, okay? So you got all the way to n steps over here. And you can notice that here, n minus 1 all the way to 1 is our arithmetic progression, right? That also can be calculated as well. So now we are ready to really sum up the running time. Okay? Let's now do it here. Big O, off. All right. It's going to be, first of all, let's do append. The append is going to be just constant between every step. And we know that we got exactly n steps. So it's going to be n times 1. Right? N times 1. So over here, this is about the number of steps. And this one here is just about a swap that we have to do. All right? And then plus. What about the actual selecting the minimum, right? It's going to be n plus n minus 1 all the way to 1. It's going to be n plus n minus 1 plus all the way to just 1 over here. All right? So this is about selecting. And just make a little bit more annotation for you. Think about this is the cost for the first selection. And this is the cost for the last selection. All right, and let's see what it should be. This guy here is just n. Big O of n plus, and this part over here, how do we calculate that, right? Just beginning plus the beginning term plus the end term, n plus 1, multiplied by number of terms, which will be n divided by 2, which will be n squared, right? We talked about it last time. So this will be n squared, approximated as big O of n squared. Oh, sorry. I didn't hear. Say it again. Number of steps. You mean, oh, okay. You mean here, right? Okay, sorry. I don't know why it happened, but thank you. Multiply. You mean you mean the words over here, right? Is that what you meant?
No, when you count the thing one, you need this number of steps multiple.
Okay, so here, okay, I see what you mean. So this, you mean this part here, right? Okay, so this part here, yes, this is about summation. So the first selection will be n plus n minus 1. Okay, how about this? Just to avoid any confusion, you can think about the reason I simply put m squared over there is because this guy over here, according to our definition, will be n plus 1 multiplied by n divided by 2. Right? And we know that that one there is simply just n squared. So that's why I put n squared there. That's why. Okay? Yeah. Very valuable lesson for us to learn here. We have somehow learned about selection sort without seeing any code. But it is very important to be clear about what each critical step is going to take for the algorithm. Yeah, question?
Does this only model the worst case? Because like on average, we wouldn't have to search through the whole unsorted array to find them.
This will be definitely the worst case. Are you more speaking about this last step over here? That in the implementation we might omit it? Is more what you're concerned about? Or this is the worst case?
Never mind.
Yeah, actually you will see that it's actually very tight bound for selection sort because there's no way around. You gotta go with a nested loop with this kind of many bounds. Yeah, you will see. Okay, but it's very tight bound, but it's upper bound for sure. All right, so that's about selection sort, and then we're now going to talk about insertion sort. It's going to work in a very symmetric way, but I can give you a little bit preview. Okay, so the number of steps is going to be very similar, except that it's going to be n minus 1 as opposed to n, but some minor discrepancy. But I'll explain to you why. That's one thing, but critical to notice. The first selection here is the most expensive one, and then it decreases. When we talk about insertion sort, it's going to be the opposite. The first insertion is going to be the cheapest, and it will keep increasing until we get to the most expensive insertion in the last step. That's something we'll see. All right? Insertion sort. All right. Let's now talk about insertion sort. And that one there, when I generalize it, I'm just going to present in a slightly different way so you can see which one you prefer. So the idea will be we got to keep getting the first element from the unsorted portion. So getting or choosing or selecting, whatever you like. So let's say stick to getting. Okay, I'll stick to this word, getting, get. I want to keep getting the first element from the unsorted portion. For example, if I start the unsorted portion like this, I want to get the first one, just this one. I don't need to do any selecting minimum, no. So this part here is a constant operation. Always, like a pen in the selection sort case. And then I'm going to somehow insert this element here into the sorted portion so that the grown sorted portion remains sorted. That's a very critical part, okay? But also what we got to work out is, when we do the insertion, what's going to be the worst case? That's something I also need to generalize in a moment. And one thing to note, when we first start the array, we don't necessarily have to start with the sorted portion being empty. It wouldn't impact our understanding. So for now, I'm just going to start with the first element there already sorted, right? It's by itself. It's okay. Okay. So the sorted portion here, to begin with, just size 1. Let's now talk about the different steps, and then we'll generalize it. Okay, I don't think we need this over here. And I'll just copy that. All right, the first step, we're going to follow faithfully about the description there. First of all, we're going to insert some element that we get from the leftmost element in the unsorted portion, which will be just this one here. Just want to get it. Okay, let's talk about this kind of a worst case intuitively. Okay, in this case, you can think about, I want to insert this one here into this area over here. Okay, I want to insert this element here into this area so that the sorted portion can grow by one element. Now, I got, in general, two possibilities. Should I insert one into here, or should I insert one into here? The one should be chosen should be here, because that's how the sorted portion will remain sorted. Let's do that first, and then we'll talk about running time. So what I will do is I'm going to get a new array over here, right here. And then I know that this one here should be inserted right before 3. Right? So think about 3 is being shifted to the right. So now when I talk about shift, you can kind of sense what the running time might be in general. Well, we'll talk about it. So what's going to happen is we're going to get 1 here, 3 here, and 4 and 2 remain the same. So what we get is we get this. 1, 1 and 3 over here. And then we get 4 and 2 right here. All right. Insert A1. That's what we just did. And let's continue with the next step. To really get the element, we're going to get the leftmost element from the unsorted portion. Constant operation. Just go there. And then that one there is going to cause us to insert A2. A2. Now, this will be easier for you to see the worst case. Let's imagine this. Let's hide the contents over here. Okay? Let's say in general. I got some sorted portion already over here. I want to insert index 2 element into here. We talk about insert on Tuesday. Now, I got 3 possibilities. I can either insert the element into the beginning, I can insert that to the middle, or I can insert that to the end. I got option number 1, option number 2, and option number 3. Which one seems more expensive to you? 1, 2, or 3? Never mind. Okay, anybody? Take a guess. It's okay. 3? 3 actually not bad. Because if you want to insert into 3, you're just going to swap the element directly. You don't need to shift anything. 2, well, for 2, yes, you got to go here, but you only got to shift one thing to the right, right?
I think it's 1 because in the worst case scenario, if it's way bigger than the rest of the array, then you have to do the shift 1.
Yes, exactly. Okay, that's very good, Diago. So I'll get to exactly what he really meant. So here, if I want to insert that, well, let's say, if this element here, we don't know. If you want to insert it to the beginning, that means that one will be index 0. This one becomes index 1. This one becomes index 2, right? You got to shift the whole block to the right by one position. Okay? Just use this example to say the first time, but I'll say that a few times. Okay? All right, so now what about in this case? This case, we're lucky because 4 here is already the maximum for the new sorted portion. So 4 can just be here. All right? So now what's going to happen is we're going to get a new array over here. And then we're going to get 1, 3, 4, and then 2. Okay, nothing changed, but we're just going to get 1, 3, 4 as the sorted portion. And then we're going to get 2 as the unsorted portion. All right. One very important point for us to know. We are now reaching the starting point for the last step, which I'm going to highlight. So this part here, we know that the sorted portion is exactly one less of the array size. So this one here, you can say the size of the sorted portion is exactly n minus 1. In this case, n is equal to 4. N minus 1, we got exactly 3. All right. So now we can do the last step. The last step is going to involve something very similar, which is going to insert 3 here, right? That's the leftmost for the unsorted portion, right? So we're going to insert A3 in here. You can now see the insert over here. Should be the most more expensive than the initial insert, because now it's a bigger area that we want to insert into, right? So now 2 will somehow have to go here. Once 2 go here, we got to shift 3 and 4 to the right by 1 position, right? Let's now put it down, and then I'm going to generalize it. So now after this, we're just going to get 1, 2, 3, and 4. And that'll be the last stage over here. That's insertion sort. The number of steps, just 1 less than the selection sort conceptually, but that shouldn't impact the bounds. All right. If no question, let me now mention one very critical understanding for us. We want to know exactly how to visualize the worst case for the insert, right? Let's now talk about it. Okay. Worst case for insert. So once we work it out, we will be able to count for individual step for the worst case. Okay. Let's now talk about just in general. If you got your input array, and somehow we are in the middle of somewhere for the insertion sort, somewhere in the middle. And then, of course, we got some sorted portion, we got unsorted portion as well. Let's say this is the sorted portion right here. Okay, let me use a slightly different green. This is a sorted portion right here, and this is the unsorted portion. And specifically, I want to also point out, so this is the leftmost element in the unsorted portion. All right. And I'm also going to write this to say this is the old sorted portion. It's going to be grown by 1 at some point soon. All right. And we talk about insert. What will be the worst case? The worst case is going to look like this. The worst case will be the element that we got from the leftmost in the unsorted area. That one there happened to be smaller than every element in the existing sorted portion. In order to insert into it, it's going to come here for sure. That's the minimum one. And then what about the rest? They're going to be shifted by exactly 1 position into the new sorted portion. That's where the expensive part can come from. All right, let's now put it. So I'm just going to put it here, exactly over here. And then we got this. Okay, let me now make it very clear. Think about, first of all, this guy here that we want to insert, it happened to be the minimum. So right here. That's the one we inserted. And what used to be the sorted portion will be shifted entirely into this block over here. If you think about how we did it for the insert into for the array, for example, index 0 should go to index 1, index 2 should, index 0 go to index 1, index 1 go to index 2, etc. That's a shift. That needs a loop. That'll be the worst case. Yeah?
We have the sort of set up like it's a array data structure. What if we had it set up more like a linked list? So rather than having to shift all the elements, we just appended it to the front at like x minus 1.
Yeah, I would say let's now focus. I see exactly what your question is. I can definitely revisit. It's an interesting one. So the question was, what if we change the array structure here into linked list? Is it going to make a difference? I'll rather not touch upon that just yet, since we don't even know what a linked list is. Let me revisit that maybe a little bit later. Okay, I'll keep that in mind. Okay, it's a good question. But let's focus on the array. Okay, for the array, shifting is expensive, right? So shifting this into this, expensive. All right, let's now keep this highlighted, and then we can now summarize the runtime in a table. Okay, and then we're going to do that. Right, so rather than doing that like before visually, I'm just going to use a table to show you different flavor. Okay, I'm going to use a table here, and the table is going to have several columns. The first column, I'm going to call that just the step. We're going to keep track of the step number 1 all the way to whatever. And then we want to say the element we want to get from the leftmost element in the unsorted portion. And also the next column will be the size of the sorted portion. The reason that we want to consider this is because, let me show to you. Remember the worst case that we just talked about, right? The sorted portion over here is going to be the most expensive one to grow if we have to shift everything to the right by 1 position. That's going to be exactly the size of the sorted portion, right? So I'm going to write here, insert over here. The maximum cost will be just equal to the size of the sorted portion, right? That's why we got to keep track of it. In the beginning, if the size is 1, cost is 1. Cost is 2. All the way to the cost is n minus 1, getting larger and larger, right? So finally, we're going to put what's the maximum cost for insert. That'll be the most important column to really get right, so we can sum up together. Maximum cost for insert. All right, let's now fill out the table row by row. Step number 1, we want to get A1. The size of the sorted portion is 1. Accordingly, the maximum cost will be just 1 to shift 1 element to the right. Right? Row number 2, step number 2. We will get A2. Size of the sorted portion is 2. Accordingly, the maximum cost will be 2 when we want to shift everything, all the 2 elements to the right by 1 position. A2, and then 2 and 2 here. All right, let's do one more. Right, you can see here, if there's 3, choose 3, right? And etc. I got 3 here. I got to choose A3, and then 3 and 3, right? And we can say dot, dot, dot. Let's see what's going to be the last step. The last step is going to be something like this, where we got exactly 1 element in the unsorted portion, meaning that the sorted portion is n minus 1 elements, right? So what we're going to do is we're going to get exactly n minus 1 left over here. And then we're going to get a cost accordingly n minus 1. That means we're going to shift all the n minus 1 element to the right by 1 position so that this one here can be inserted to at the very front, right? That's a maximum cost. What will be the step number then? You go 1 to n minus 1, right? So that should be n minus 1, right? That's a pattern. So that means we don't really have like n steps as we saw in selection sort. That's okay, just 1 off. And this one here should be a of n minus 1. This is also important because a of n minus 1 is also a valid index. There's a maximum valid index for the array, right? A dot length minus 1 idea. So now we got 1, 2, 3, all the way to n minus 1. Again, we got arithmetic sequence. The interesting bit is now we're going from 1 all the way to n minus 1. For selection, so we got n all the way down to 1, right? It's different. Let's now write down the running time to conclude. We go off. So we got n minus 1 steps in total. Okay, n minus 1 steps in total. First of all, I'm going to put n minus 1. This is about the steps that's required. And then I'm going to say times 1. So this one will be about choosing or getting. Right? So every time I want to choose, I choose this, I choose this, I choose this, right? Constant time. Plus, now I just got to sum up all the costs over here. 1 all the way to n minus 1. We know that it's n squared, but let's write down. It's going to be 1 plus 2 plus all the way to n minus 1. Right? We know pretty well this one here will be, for example, 1 plus n minus 1, beginning and the end, times n minus 1, n minus 1 terms, divided by 2. Very quickly, we'll just approximate. N here times n here, we got n squared. It's going to be the highest power, right? So what we get is, finally, equal to big O of, this one is like a n minus 1 plus n squared. Highest power, n squared, so that'll be big O of n squared. So that's the asymptotic upper bound for insertion sort, which is equally efficient as selection sort. And notice that we haven't seen any Java code just yet. That's a very important skill to have. When you describe your algorithm, when you are trying to design your algorithm, you really don't have to write code first. Just kind of sketch the critical step first and get some sense from there before you write the code. Just by doing this, you can already kind of decide which algorithm you may want to use. But of course, in this case, it doesn't matter which one you use. Asymptotically, they are the same. All right, any question about this one here? Yeah?
I'm not sure like how to like big O notation this would be, but would it be possible if we at the midway switch from insertion sort to the selection sort, since it would be 0?
What do you mean the midway?
Well, because you said as we increase in steps for insertion sort, it becomes like it takes more time to complete a step. But as we go through the selection sort, it becomes faster, right? Like for each step.
I see what you mean. Let me think about it. Yeah, let me think about it. Otherwise, if I sketch something random, your fellow student might just get confused. Your question basically is about, can we say we start with selection sort, and then on the halfway through, when it gets more expensive, can we switch to insertion sort?
Yeah.
Let me think about it. I'll get back to you. Okay, thank you. Good. All right, any other questions? Good. Okay, so now we can see some Java code. Oh, all right. So let me just see this one here. There we go. So let me see what I want to do over here. So we got selection sort. Okay, insertion sort. Okay, good. Okay, let's see some Java code. There we go. All right, so this is the Java code for selection sort. You can also find the source code in the lecture site. It's already made available to you. Okay, so here there are two things we can do. Number one, we can trace it, which I'm not going to do. You can do it yourself. It's part of the exercise. But given this, let's derive its asymptotic upper bound very quickly. All right. So before we try to derive the upper bound without having the code. So now we are trying to derive the upper bound without knowing the logic of the code. Right? You can see we're doing things that just focus on the bounds. Let's do this one together, and then I'll give you several exercises at the end. Don't even think that's selection sort. It's not relevant. We're just going to analyze the code structure like how we did last time. All right? Got some input array, and we got some n. Again, as usual, n here will just be a.length. Right here. All right? And then you can see we got some nested loop structure over here. Okay? I'm just going to do some annotation, and we'll be ready to start counting. First of all, I want you to look at line number 3, and also line number 6 to line number 8. As you will see from the indentation here, we are suggesting these lines are not part of the inner loop. They are not. So that means the number of times we're going to execute line number 3 and also line number 6, line number 7, line number 8 depends on how many iterations there will be for the outer loop. Right? That's number 1. So for these two, execute it according to the values of I, which is the outer loop. Right? We're going to enumerate that in a moment. On the other hand, if you can see line number 5 here, this would be the one that's going to be executed for every combination of I and j, which we also saw some example last time, but we're going to do it again. So this one is going to be executed according to the values of ij. And let's look at individually. Line number 5 itself is just about if statement and also variable assignment, 1. Also for line number 3, variable assignment, just 1. And for line number 6, 7, and 8, by the way, it's swap. Right? I talk about swap when I talk about selection sort. You can look at that yourself when you do the tracing, also 1. And let's now try to trace, well, to enumerate the pattern for I and j, which will be something you have seen already, but let's do it. Okay. So now we're going to look at the patterns for I and j. So I'm going to put I here. You can see I bound is going to start from 0 all the way to n minus 2. Right? It tells you explicitly, right? Less than or equal to. It's going to be 0, 1, 2, all the way to n minus 2. What about j? Oh, before that, how many iterations are there? N minus 1. All right, guys, got to review that. 0 to n minus 2, and we'll talk about that formula, right? Okay, that one will be n minus 1 iterations. I'll highlight it. You got to make sure you know how to do it. All right, let's now enumerate the value for j. For j here, so now j is going to be starting from I, right? Looks like triangle, right? The one we talked about. So when I is equal to 0, j is going to be from I, which is 0, 1, 2, all the way to n minus 1, all right? When I is equal to 1, it's going to start from 1, 2, all the way to n minus 1. When I is equal to 2, 2, all the way to n minus 1, right? What about the last row? When I is equal to n minus 1, sorry, n minus 2, what should be the value for j? How many values? 2 values, right? Not 1. N minus 2, n minus 1. So if you try to draw that, it's not a perfect triangle, but almost like a triangle. All right, so what we got to do is we have to now count. How many possible combinations there, right? We either got 0, 0, we got 0, 1, we got 0, 2, and etc., right? How many do we have in the first row? 0 to n minus 1, n, right? Hopefully you see what I mean here. So now this will be n. And from 1 all the way to n minus 1, we got n minus 1. 2 to n minus 1, we got n minus 2, right? Here, n minus 2, n minus 1, 2, right? So now we are ready to do counting. Think about this one here is nothing new, nothing to do with the sorting itself. I'm just analyzing the code structure. Right? I can give you something arbitrary. Okay? Let's now figure out the big O. So it's going to be the big O of, since we got n minus 1 iteration, I'll start with that. I will say n minus 1. So this one will be the number of iterations for outer loop. So the number of iteration of the outer loop. And for the outer loop, we're going to execute this one here and this one here, right? Both of them just 1. 1. So it's going to be line number 3 and also line number 6 to line number 8, right? Also, plus. We're going to execute line number 5 for as many times as necessary for the combination of I and j, right? That one there is going to be here. Add up n plus n minus 1 plus n minus 2 plus all the way to 2. And then times 1. The 1 here is really line number 5. And this part over here is this part here, right? What would that be? n squared for sure, but let's see a little bit more precisely. Beginning term plus the n term. How many terms do we have? From n all the way down to 2. N minus 1. Okay, good. Divided by 2. And we don't need to go any further because n times n here is going to dominate, n squared. This part here is just big O of n squared. All right, and simplify a little bit. Big O of n minus 1 plus n squared. And we got big O of n squared. We have got consistent result as when we derive it from the visual sketch for selection sort. So this one tells you when you want to derive the asymptotic upper bound, you can either do visual sketch and derive from there. Or you can look at the code without understanding logic and do it from there. If you want to do tracing, that's another story. Yeah, question?
Sorry, quick question. I'm a little bit lost on the orange part.
Yeah.
Is that the formula for the geometric sequence? N plus 2 times n minus 1 over
Okay, so this one, you mean this part here? Oh, this part here. Yes, arithmetic sequence. Yeah, the formula is if you want to sum them up together, it's going to be the beginning term plus the end term multiplied by the number of terms.
And then the number of terms corresponds to the algorithm.
Yeah, you can think about the number of terms over here. Yeah, like either you can look at n minus 1 here. Well, think about here. We are going from n all the way down to 2. How many numbers do we have? We got n minus 1 number. Yeah, think about it, okay? Guys, you got to be very fluent about seeing how many numbers are there when we have a sequence here, right? We've seen many examples, okay? May Diego, get back to me if you still haven't got it, all right? Okay. All right, so that's about selection sort, all right? Guys, exercise for you. This is the piece of code for insertion sort, but you don't even need to worry about the name. Given this piece of code, can you derive the asymptotic upper bound? Okay, exercise for you. I'll put it here. Exercise. And then, let's see back to the slides. I do have more exercises for you. And then we can take a short break. And then we'll do a little bit of linked list today. A little bit, okay? Just bear with me a few more minutes. All right, so we'll talk about selection sort and the code. And also we'll talk about insertion sort and the code. So the asymptotic upper bound will be up to you. You got to derive it on your own. And then some exercise to start with. So let me go over that with you. So let's say given a piece of Java code, like a selection sort, insertion sort, you will be expected to derive the asymptotic upper bound, which we did for selection sort. Okay, number one. Number two is also important. Don't abandon the importance of tracing. You also need to know how to trace nested loop for runtime execution. All right. We have done number one already, right? We just did it. And then we also discussed how intuitively the two sorting algorithms should work. But now you want to go down to the code level and see how the variables really get changed between iterations. That will be your task. So now you'll be expected to trace the Java code, selection sort and insertion sort, using different approaches. Right? On the paper, you gotta basically look at here. I will leave these two pages clean for you. If you look at selection sort and also you look at insertion sort, right? I already got some table over here for you. You're going to trace it to see how the values of J, for example, mid-index, etc., how they're going to change between iterations. That's what you're required to do. All right? I got selection sort, I got insertion sort. You got different variables to trace. Okay? That'll be the paper trace. And then for that one there, if you want to look at the solution, so I got some recorded video to actually go over with you about tracing. You can look at that if you really get stuck, not too sure about tracing. So in the written test or exam, I might ask you some question about the code, like this complexity. So it's good for your learning and also good preparation for you to do this exercise. The videos are optional if you're confident about tracing, but it's there for you. The third one, it will be, you want to also trace it by using Eclipse debugger. There's also a video to show you how to do it. All right, you got to do both the paper and the Eclipse. Okay. Let me know if you got trouble doing it. One final thing before we take a short break. So what we want to do now is to think about the exercise. Okay. Before that, so we talk about selection sort, insertion sort. Asymptotically, they're both quadratic and square. They're equally efficient. And also we got the more efficient algorithm and login is going to be the merge sort and quick sort and heap sort that we'll talk about later. For now, you don't need to worry. Just know that there are indeed some more efficient and faster algorithm that we're going to learn about later. Okay, the final exercise about a sorting algorithm goes like this. Okay, and I'm just going to sketch that quickly to you about what you should do. Okay, if you kind of remember in general, that's how the algorithm should progress, right? For both insertion sort and selection sort. We basically got the beginning, for example, the sorted portion is the smallest until it gets to the entire array. So now I want you to try the following modification. Number one, the sorted portion is maintained on the right. What does that mean? That means, for example, rather than this, I'm just going to erase this for now. Eventually, we still got to all green. After the first step, I want the sorted portion to be here. After the second step, I want it to be here. After the third step, I want it to be here. You should maintain in a different end of the array. All right? That's the first modification I want you to do. And the second modification, I want to change the sorting order. Rather than non-descending, I want non-ascending. The order will be non-ascending. So these are the two modifications I would like you to make to see how you should change the code accordingly. You got the source code already, so that should be rather straightforward to get started. Okay. And if you look at this slide here, slide number 9, it's actually saying just specify the exercise I just spoke about. All right, any question? We good? Okay, very good. I think we only got 2 minutes left. It's not feasible to talk about linked list today, but we are not too much behind from the morning section. I only did like a 3 minutes introduction today. So I would suggest you should really review up to and including slide number 9, and then we'll start you fresh about linked list. Before you go, let's take attendance, and then that's it. All right.